Hello. This lecture will cover pages 50 through 53 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 7b, First Order Transient RL Circuits. Starting on page 50, we're going to do the same thing here with the inductors that we did with the capacitor. And you're going to see a lot of parallel here. The only thing that's different is pretty much the time constant, but inductors in DC circuits, the transient effects. Remember, a transient are changes in voltage or current that happen in relatively small periods of time, and after this transient phase passes, you are said to have reached steady state. Just like the capacitor, the inductor has two transient states possibilities. It has a charging state that looks like this, where it charges to a final value in 5 time constants. Time. Don't forget, this is x of t, voltage or current here. That's your charging exponential, and there's the equation for it, where the time constant tau here is L divided by R in seconds. And then it has a discharging. This is time. It discharges from initial value down to 0, decays, has this mathematical form here. Here's your x of t out here. Remember, we said this final value here in the one equation we called K1. Okay. So this was that final value, K1. And 5 time constants took us to a final value here, and 5 time constants took us to a final value here. Okay. Incidentally, this was the K2 value down here. There was the K1 value, and this is the K2 value right here. The charging and discharging curves all follow the same exponential time response during the transient phase to get to steady state. We've seen this before. Here's the observation we made before. You would make the same observation. Real quick, x of t as a final solution for a first order linear differential equation. We'll get these equations coming up here, but we're going through the basics of this now. K1 plus K2e to the minus t over the time constant. That's a general form where x is voltage or current. You evaluate x is 0 up here. Just use this and work with this as you go through to get this final general equation. X is 0, put 0 in for t up here, you get K1 plus K2. X of infinity up here is simply equal to K1 because this whole term goes to 0, e goes to 0, K2 times 0 is 0. Therefore, you can see what K2 is equal to from this equation. And make those substitutions, you can see K2 is simply equal to x is 0 minus x of infinity. So that is your K2 term, which we're going to put in down here, which is right here. We put a K2 in right here. We just showed K2 in terms of what? In terms of x a 0? In terms of x infinity. That's all you need to find out. On these circuits, you find out this, using common sense. Plug them into here. There's a general expression. The only difference is time constant is L over R in seconds. Solving for current or voltage with these inductive circuits. Here's an example circuit. For this circuit, I want you to determine the current, IL, if the switch is closed at t equals 0. Then find the value of IL at each time constant 1 through 5 using the equation and compare it to the results you get on the table on page 48. I think that was on page 48. Let me check here. Looking back on page 48. Yeah, I'm pretty sure. No, it wasn't on page 48. I'm glad I checked on that. You're going to be looking at the table on page number 51. So we need to change that to page 51. Or any place I had the table. So here's the circuit. There's no initial condition here. There's no initial current here. This is open from minus infinity up to t equals 0. At t equals 0, you close that switch. And I want to know the current in this inductor. I want to know the current here. I, L of t. Let's use some common sense here before we go through this. I want you to take a look at this, and is that current going to have a rising exponential or decaying exponential? Well, it's going to start out at a particular value. When you first close, when you first close this switch, that's not true what I just said. When you first close this switch, that's going to look like an open circuit. It's not a capacitor. Capacitor would look like a short circuit, but it's going to look like an open circuit. So when you first close that switch, you can't have any current. So I, L of 0 minus is what? Well, if that switch open, the current's 0. That's 0. That has to be equal to I, L, a 0, which has to be equal to I, L of 0 plus. Why? Because current can't change instantaneously through an inductor. So when this circuit's open and there's no current, and you first close that, it's going to look like an open circuit. And this is all true. So you know that current is going to have to start here. And it's going to have to rise to a final value that's limited by this resistor, because it's going to look like a short at that point. So could you go from here to here without this? Sure. I don't want you to do that yet. I want you to say, right here, find the time constant. You're going to have to find the time constant no matter what here, but the time constant's L over R. L over R is 8.33 microseconds. There you got your time constant. Now what you do is you evaluate IL of t using this general formula I gave you, which is I of infinity. What's I of infinity going to be up here? Well, it's going to look like a short circuit. So it's going to be 12 divided by 1.2K. That's the only thing limiting that current. I made that calculation here. It's the final value of current. It's 10 milliamps. I of 0 is equal to 0. For this reason I just told you up here. I'm just making the substitution of this value here and this value here in that original equation. And this is what I end up with. I end up with IL of t is equal to 10 minus 10e to the minus 12 times 10 to the 4th t. That's just this inverted. I just bring it to the top here. Rather than putting t over 8.3 times 10 to the minus 6th. Sometimes you'll see it all in the numerator here like this, in this exponential, in this exponent of the e term. So that's the form. You can see it's a rising exponential form. Put in t equal 1 time constant, 8.33 microseconds, make a calculation. Did I do that here? Let's see. No, I didn't. But I want you to go ahead and make a calculation for 1 time constant. Take 2 times this and plug it in there, and 3. And see what you get for these values here, and compare them to see if they are equal to 63.2%, and 86.5%, 95.1%, and 98.1%, 99.3% of that final value, which is going to be 10 milliamps. That's the final value. It'll give you, everything will come out nice there. You'll be able to see that, I think. And then you do that once in your life. What else in that? Just for the heck of it, I didn't ask for this, but what would the voltage be? What would the form of the voltage be I want to know voltage across the inductor with respect to time. Rising exponential or decaying exponential? Well, you could go ahead and just make some calculations and use this form right here. Take your time, write this on a piece of paper, calculate the voltage at time equals infinity, then calculate the voltage at t equals 0, and put it into this equation. And see, once you put it into this equation, see if these two terms here, see if this cancels out. See if this value here cancels out with that value, and all you end up with is a decaying exponential. Because what should the voltage look like here? Well, initially it looks like an open circuit, so you're going to have a voltage there. And then as time goes on, that looks like a short circuit for voltage now. That's a decaying exponential. So you're going to have your K2 e to the minus t over tau, where tau is L over R. So, I mean, you either get this first and you go to that, or you get this and you go to that. But you should be able to rationalize whether you have charging exponentials or decaying exponentials, whether it's a capacitor or an inductor, and then more specifically, whether it's voltage across either one or current to each one. Until you see that, and it takes some time, but you just think of the basics, and it's pretty easy to get these equations. Here's example 2. I want you to find the voltage across that inductor. It says here, find VL, the voltage across the inductor at 10 microseconds. This reference to page 48 here. Let me see what I was looking at there on page 48. No, that's not a reference I want you to look at on page 48. I want you to be looking at page number I want you strictly to be looking at page number 51 and see if you get that same answer I got here, or whether you can go straight from here to here. That's page 51. And example number 3. Find a current, I sub L, at 10 microseconds. I want you to know the current here. 10 microseconds after that switch is thrown at t equals 0. Oops. I sub L. I sub L. All I did here is I could go straight. I could go straight here to here, and you might be able to do that. Okay, or at least straight from here to here, straight to that equation. Then make the substitution for t and get your answer. So you should be able to go straight from here to here. All I did was use the observation. All I did is use this formula right here again, and there it is. I evaluated the current at infinity, and I evaluated the current at 0 plus, understanding that the current at 0 minus and the current at 0 and the current at 0 plus are all the same, because it's an inductor. Once I get this value and this value, I just substitute them in to this equation right here. And it leads to this. Once you see that, you can start going from here directly to there. I had to calculate time constant though. The time constant turns out to be 10 microseconds. And I want to evaluate at 10 microseconds. That's one time constant. So I'm evaluating the current at one time constant, 10 microseconds, because that's what the time constant was if you figure out L over R here. It turns out that in one time constant, I should be at 63.2% of the final steady state value. This is a rising exponential. I'll bet you 9.48 is 63.2% of 15. How can we check your answer in example 3 by using example 2? That's the same circuit. We're just finding voltage up here and we're finding current down here. You know how you could do that? I want you to think about that for a minute. Current, an inductor, with respect to time, is equal to L di dt. Let's have some fun here. Oops. The voltage across the inductor. The voltage across the inductor with respect to time is L di dt. So I want you to go ahead and take the derivative of this guy right here with respect to time. Take the derivative of this function right here with respect to time. And I want to see if you get that. 15e to the minus t over 10 times 10 to the minus 6th. Now that's more or less using example number 3. That's using example number 3 to check your answer with example number 2. But there's another way. There's a way you could take example number 2 and verify example number 3. Think about that. If this right here is the voltage, this right here is the voltage across that inductor with respect to time. And I want you to go ahead and I want you to use that example to check the answer down here. Do you see how you can do that? I showed you how to take this up here, this here, and get back to this point. So that concludes the lecture, and the next lecture we're going to show you how to develop these equations using your differential equations to develop these response equations using the differential equations. That concludes the lecture.